Okay, so today we are not continuing from what we have left in coding lecture, so this will be a pattern. If you have taken 449 last semester, you should know like sometimes the coding lecture and like the theory lecture, they are disjoint. So in coding lecture, mostly we will learn the transition from NumPy to PyTorch. And in the theory lecture, we'll continue the theory here in the introduction to machine learning and how we make use of the optimization theory we learned from 449 last semester. So let's do a review. So first is the goal and the setting. What happened is given, so we're solving this problem, or we try to solve this problem, is given some data. So the data is given in pair. So we have a vector x, and we have a label, or say a target y. And so in the machine learning context, we will normally view people dubbing this x as has the name of features. This one is the name of target or label. Okay. And let's assume we have total capital N those samples. And what we want to do is we want to build a function h takes input of x as parameter w such that this is our model's output. Okay. And or say you can, some people call this predictions. And this is we hope. Okay. So we want to build a function that can approximate the actual label. And this is the actual label for target. So, and many people call this ground truth in the statistics context. So this is our goal. And like our workflow is as follows. So given the data, we choose the loss function. Okay. We build the model. We choose the loss function. We train and we validate. So in last week, we've learned this part. We mentioned briefly this part. Okay, so let's recall what loss function is. A loss function characterizes the difference between y hat and y. This is our model's prediction, and this is the actual value. It basically gauges how different our model prediction is with with respect to the prediction. So what we want to do is we want to minimize this distance. Okay, or say minimize this difference. So a simple example, so we'll use as today's lecture's example is what we called the square loss. So mean square loss function. Okay. So it's given as follows. So I'm going to write down this capital L. And what I want to emphasize is so loss function variable is W, which is our model. Okay. Model's parameters. So in our model function, all right. So in our model function, the weight, or say the parameter, are our parameters, and this is the input, which is independent variable. But in the loss function, keep this in mind. What loss function does is characterizes the difference between this and this. So it uses the model as our input, because this basically represents like the predictability, or say predicting power of our model. So the loss function's variable is a weight, or say the parameters. So it's defined by the mean of, we just sum up the samples and we use the square difference between between y hat and y. Basically is we just take the difference, literally the difference between our model's prediction and the actual value. We measure how far apart they are, and we want to use optimization to minimize their distance. So this is a theory behind it. If we have our dimension, okay, so if our dimension is n is 1, then y hat, sorry, we have a I, superscript I on top. So when the dimension is 1, both of them are just scalars, are just values. So this is nothing but just the absolute value of the difference, and then we take square, and this will be in today's lecture. Okay. And when we have dimension greater than or equals 2, this is just the 2 norm. So basically we have like these two are vectors, but because we have this hat, so I'll skip this little arrow here just to make it clearer. So this is the same thing as the summation from j, which is the j from 1 to the nth dimension. Basically this is component wise. So this is we summing up all components of the vectors. So we'll consider this case, all right, in our lecture today. Next is training. So next step is training. In this step, we'll use, whoops, pardon my spelling, training. In this step, this is where we use optimization. So this is the main topic of this semester's class. So we'll learn the theory, like when it is convergent, and we'll learn how to code them. So for example, even though there are many like built-in optimizers already for the optimization in, for example, the PyTorch and NumPy, very mature packages, but this semester we'll learn how to come up with our own algorithm and implement it. So this is the main topic of this semester's class. And the simplest one, so we're looking at gradient descent. Okay. So here I'll do a background poll. So if you have seen this before, and it's anonymous. Okay. So which is gradient descent. All right, cool. So far, it seems everyone have learned, maybe except a few students. So I have posted like last semester's video, like on optimization, which is about gradient descent on Canvas. So even though it's a little bit blurry because many videos are using the school's camera, which claim to be high resolution, but is not. Okay. Thank you for the polling. And but let's brief review it. The gradient descent is, keep this in mind. Now what we want to do is we want to optimize, or say we want to minimize in this special case. We want to minimize the loss, or say we want to minimize this difference. Okay. So we want to minimize this difference. We want to minimize our model's prediction and the actual ground truth. We want to minimize this. And what we do is we minimize this function. Okay. So which is, we use at the nth iteration, we have Wn plus 1 equals Wn, subtract, this is gradient descent, alpha times gradient with respect to W of our loss function. So this is gradient descent. Alpha is called step size or learning rate. So if you read PyTorch's document, so it tells us this is learning rate. But in the context of optimization, example in our textbook, we normally call this step size. And it's a type of what is called a hyperparameter of our model. So it is a hyperparameter of our model. And we want to tell the difference between parameter and hyperparameters. So parameters of our models are W. But this learning rate is one hyperparameter. So it does not directly determines what the model is like, but it governs like how well we can train the model. So the parameter of the model are like the weights of the neural network, but hyperparameter determines like how we train the model. So okay, so it's one hyperparameter, and we can have other hyperparameters. So the parameter W, and basically this is our the gradient descent. Okay, and in the context of So the neural network, whether it's deep or not, so deep just means it has many layers. Okay. So in this context, the key is how to find this derivative. Okay. So how to find this derivative is actually one of the two pillars of modern machine learning. So there are two pillars of modern machine learning. I mean, even though so the neural network model actually is there like 50 years ago, but until recently, until maybe say a recent 20 years, people are able to so-called train these network. So the pillars of a modern machine learning is the first one is called backpropagation, which we'll learn today. Okay, propagation. The second one is stochastic gradient descent, which we'll learn in our next module. Okay. So today, basically, our main topic is to learn how to do backpropagation for neural networks. And let's look at some definition. Okay. What it is backpropagation. So the definition is pretty simple. It's just a fancy name for chain rule. Okay. So first of all, I assume every one of us have heard or have learned the chain rule, all right? So if you forgot chain rule, don't worry. So if you Google YouTube, there are like perhaps 10,000 videos on how to do chain rule. So don't worry about that. And I do recommend one channel. So I'm not sure if you have ever heard of it. So of course you can go to Khan Academy, but there is a nice there is a nice channel called 3 Blue 1 Brown, and I highly recommend this channel. And so I will be posting links of some of the video of this 3 Blue 1 Brown channel on our canvas. So this guy is a great explainer and is a much better instructor than me. So I highly recommend you guys watch some of the video there. So today we will learn how do we do this backpropagation. It's essentially chain rule, nothing fancy. And let's review chain rule. Okay. So for example, if we want to take a derivative of this, right? So this is a composite function. And if we think about this composite function, it actually has two layers, all right? So why I'm saying it has two layers is because if you think about this is the input, right? The input goes through the first layer, which is G, and then the G is like the output of the first layer, which goes to F, which acts like our second layer. So let me add here. So G is like our layer 1, and F is like our layer 2, which is exactly like neural network, like layer by layer. And we have here we have composite function. And what the chain rule does is we take derivative from the outermost layer, and then we layer by layer, we reach the innermost layer. So for example, the first one is f prime, the outermost layer, but uses the inner layer as input. So let me add a remark here. So this is a derivative of outer layer, but the input is actually the output of the inner layer. And this actually characterizes the chain rule by like most precise way to characterize the chain rule, which this is the key, is the input of the outer layer function, okay, is actually the output of the inner layer function. So, and then multiply g prime of x. So this is a derivative of the inner layer. And now let's try to apply this formula to neural network we have learned. So we use this a simple three layer so network. So so example, okay, so we use this 3-layer net from coding lecture 1. So we have the following network. This is our input layer. We have 2 neurons. So our input is a vector of dimension 2. So this is our input layer. So input. And this is our hidden layer. We have 3 neurons. And our, so this is called a hidden layer. And this is our output layer. Okay. And we can connect them. So for example, so it goes here, it goes here, it goes here, it goes here, and it goes here, it goes here. So every single neuron or say perceptron from the hidden layer is connected with the input layer. Okay, and lastly, we have a single output layer which accepts input from the hidden layer. So if we review the vectorized notation, we have so L is like the L layer. Okay. So and our activation function, so sigma, let's use F. So F is our activation function. So in the coding lecture, we use this. We used ReLU as our activation function, and so using vectorized notation, we can have our function represented in the following way. So for example, in our layer 1, so let's use this notation. So this is our A1 of, let me put this not bigger. So A1 of our first layer, and this is A2 of our first layer. Okay. And then the output, so by the way, I want to emphasize, this one is essentially our input first component of the input. And this is the second component of the input. So we have our input is X vector, which equals X1, X2 transpose, which is a column vector. And the hidden layer, the first unit we have, this is A1, but the second layer, okay, let me put the circle bigger. Oops. So we have, this is A2, A2 second layer, A3 second layer. Okay, so lastly, we have, this is our output, which is A1, the third layer. So using the vectorized notation, we can review what happens is, so we have our first layer, the weights represented here, which is W. Let me use blue to represent. The weight matrix associated with this layer is W1, and the bias is B1, okay, bias vector. And the weight associated here is W2, and the bias, we only have one bias this time, which is B2. So now let's represent our function again. So what happens is the input goes in the network, okay? So we have our A2, which is, I'm sorry, Z2 is, we're using first layer's weight multiply with our input vector. So this is our input vector. Then we add the bias vector, which is B1. Okay. And let's track the dimension. So this is a column vector. It's a 2 by 1 vector. And our weight, the weight matrix of the first layer to the second layer transforms a vector from 2 by 1 to 3 by 1. So this matrix should be of size 3 by 2. Okay. And plus, and the B vector is just like for every, so the bias for every single perceptron or say neurons, we have one bias. So it is a 3 by 1 vector. Okay. And the second, in the second layer, we have 3 units, let's say 3 neurons. Then we have 3 by 1 vector in the second layer. And now, after we get this linear combination plus the bias, Z2 is being put into an activation function. So it's A2 equals activation of D2. So this is a first layer, layer 1 to layer 2, all right? And then we have layer 2 to layer 3. What happens is, so we do similar. So the 3 equals W2 times A2, and plus we have only a single bias. And for this part, we just don't have activation, okay, for simplicity. And what happens is we just do A3, 1, A3, which equals Z3. And by the way, even though I'm using this vector notation, it's a scalar because it has only like one component. So okay, so it's a vector of one component. And now what happens is we put this predict, so which is this guy. This guy is our output. So output. And this is our, like the model's mechanism. It's actually the composite function of several things. So we put into a linear function, and then this guy is composed with this one. And then this one goes here, we get a linear function. And now what happens is, so finally y hat equals, which is the scalar. Okay, so let me use this. So y hat is the scalar, which is W2 times, and of this guy. Okay, but this guy is this guy. So we have this F. But Z2 is like this guy here. So what happens is we have W1, A1 plus B1, then plus B2. So this is our output of our 3-layer neural network with one output unit, or say neurons. So this is the formula of a 3-layer neural network with one output. And now we put this output in our loss function. So our L of, and because our L is a function of this, and that, so L is a function of W1, B1, and W2, B2. Okay. So we just denote this as, in short, as L. And L is defined by, suppose we only have one sample. Okay, so one sample. It is then y hat subtract y squared. So what happens is we want to take derivative. So we want to figure out. What happens is we want to figure out. We want to figure out a partial Wi of L and partial L partial Bi of L. Okay. And let's look back at this formula. So this is our composite function, and we would like to figure out these gradients. So I'll take a pause and let me just check everyone is still following. So just to be honest, in the online, this class format, because we're sitting next to a computer screen and nothing stops us from, opened up a YouTube or even, Netflix. So my goal is not to put you guys in front of a computer screen and ask you to focus like 120%. So instead, I want to give you guys like easy and relaxed environment. So think it's better for learning. So we don't have to like, give us 100% focus the nerve, which, consume us pretty fast, and in turns make us attention span very short. So thank you. So now we're ready to tackle the derivative. So what we do right now is called backpropagation, which is one of the two pillars of modern machine learning. So now let's take the derivative. Okay, let's consider this one first. So for example, let's take derivative. So partial L, partial B, which B2 is just a single number. It's 2, right? So if we want to write down, so here I'm writing down using backprop notation, chain rule. So I don't want to write everything explicitly first. What we first do is we take a look at this expression of our loss function. Okay. So what I want to emphasize is this is not a variable for loss function. Okay. So loss function uses, for example, loss function use parameter as its independent variable. So the parameters are all here. This is like our data. The loss function treats data as constant. So when we take derivative, okay, so it's taking this derivative, right? And now we apply chain rule. This is 2 times y hat subtract y times, okay, of y hat subtract y. So I assume everyone is okay so far. This is just the application of chain rule, nothing fancy. The key is, like I said here, we have to acknowledge that y is our data, is not a variable of the loss function. So when we take the derivative, partial derivative, this one is like a constant, it's gone. So this is, by chain rule, it's 2 times y hat subtract y times b2 y hat. Okay, good. So assuming everyone is good. So now let me continue. And now let's look back at the expression of y, okay, which is this guy. But we want to write it in a more like a concise way. That is a W2 of A2 plus B2, all right? Because if, so now why I'm writing this way, not the full way here, is because if we are taking derivative of the second layer, it has nothing to do with the first layer. So let's look at here. So B2 is a weight. B2 is a weight of the second layer. And now we take derivative here. Here, this term has no B2 whatsoever. Okay. And if we take B2, we get 1. So we get, this is 2y hat subtract y. So as we can see, the derivative is nothing. For the bias is just nothing but the difference between our prediction and our ground truth. So the gradient is this difference. It's kind of important. Okay, so keep this in mind. So later we'll come back to interpret this gradient. So let me add a remark here. Nothing to do with B2. Okay. And now let's do the same thing for W2. And what happens here is, all right. So what happens here is, so partial L, partial W2. So this is partial W2, which is our weight matrix. So W2 is, so let's, if we look back, so W2 is a weight matrix that maps a 3x1 vector to a 1x1 vector. So it should be 3x1 matrix. So it is. So a 3x1 matrix. And it is y hat subtract y square. So everything the same. We follow exactly here, all right? This has nothing to do with W2. So everything follows this step. We change this B2 to W2. Oops, sorry. Okay. And I do want to have a remark on notation. So remark. So if, let's say, what it means to take partial derivative or say a gradient with respect to a vector. So if we have a vector, if x is a vector, then this notation simply just means like partial f partial x1 up to partial f partial xn. So I mean, this is notation. It's pretty much like this is our gradient. So and in the context of a neural network, if it's a matrix, so if W equals Wij, and this is an m by m matrix, then a partial f partial W is also a matrix. So it's partial f with respect to W11 and partial f with respect to W1n, etc. So this is like using this notation can incorporate the derivative of matrix easily. Okay. So now let's continue here. And let me just copy this. Okay. So this is our W. And now it's our turn to take derivative of this. So we have 2 y hat subtract y times partial W2 of W2 dot with A2, okay, plus B2. So now it's a turn of, because we're taking derivative of W2, it has nothing to do with B2. So this one is treated like a constant. And we are taking derivative of, think of this. So keep this in mind, W is the 3x1 matrix. So our resulting here, this one should be a 3x1 matrix. So let me first expand it using like the full notation. So put it here. So W2 A2 is nothing but it's like a W21 A21 plus W2 A2 times A22 plus W3, and in the second layer times A32. Okay. So if we write this inner product, or say matrix vector multiplication, we get this. I think, sorry, W is wait a second. W is 3x1 matrix. That's right. W is 3x1 matrix. Okay. So 3 row and 1 column. And what happens is, so now we take the derivative of the first component. So this is whatever this is. So keep in mind, this is so this is our A3, and we have this is partial A3 takes derivative with respect to W first component, okay, and this is W of A3 takes derivative of W second component, and this is WA3 takes derivative of W first component, third component, sorry, and then we take transpose. Okay, so this is the 3x1 vector. Now we can write it more explicitly. So this guy, okay, which is here, so A3, which is this, if it take derivative with respect to this one, we get this one, okay? So this is multiply with of A12, and similarly, we get this is A22, okay? And similarly, we get this is A32 and transpose. And what is this? This is actually the output of the second layer. So this equals 2 times A2, okay? And this is a partial WL. And so this wraps up today's class. So next lecture, we'll take derivative of the first layer. So we'll even see, and then we'll summarize a formula for like arbitrary layer, okay? And the notes, so I won't post the note just for today's lecture because so I will combine this lecture with a Wednesday lecture. So we will have like a whole picture of backpropagation derived for this 3-layer method. So that's it for today. So I'll stop recording. If you have questions, you can stay here and ask like for some quick questions.